Okay, so just a real quick reminder here that I want everyone who missed the test on Tuesday last week, or it's actually a quiz, on PS4.1 on ways that you'll need to make it up. Makeup time is going to be Wednesday, November 27th. So this Wednesday during your lunchtime. Please make sure you bring your lunch to my room, and we'll complete the quiz during that time. Quiz's code you can use is 210038. If you try to use an old one because your parents got it on Dojo, then that one won't work. So you'll need to use this one. Of course, study your notes, and there's a couple of review videos in Edpuzzle, but you'll definitely need to make sure you're studying. It's 30 questions, and I would highly recommend looking at the quizzes. Okay, so what we're going to do is today is transition from last week's material into what we're going to talk about on Wednesday, which is a little bit more complex, and it's PS4.2. So it is a transition today, and talking about the question, why do instruments have different types of sound? So why is something really, really loud or really, really quiet? And then why do we have some high-pitched notes versus low-pitched notes? And so you watched a video probably on Monday in nighttime. Most of you did. Some of you may not have. That answers this question. But even if you didn't watch that video, I want you to think about a guitar or a drum or a piano, and how you can make it quieter, how you can make it louder, how you can have higher notes or lower notes, and why you would be able to do that. Okay? So you should be reviewing this in your question of the day, making sure you write the question, the date, and all that. But this is your overall answer, and it's going to vary a little bit from each instrument, but the overall length of a string, for instance, the overall length of the instrument in general, you think about the difference between a violin and a bass instrument, and how tall, you know, the instrument is as tall as a person, or a violin I can hold up under my chin. So just the length of a string, or the length of the instrument, is going to significantly change that pitch of the sound. Make it a smaller instrument has a higher pitch, a bigger instrument has a lower pitch. A shorter string is going to have a higher pitch, a longer string is going to have a lower pitch. Thickness, you think about a guitar, you think about a violin, the thickness of a string, or even a rubber band. The thicker a rubber band is, you know, the lower the pitch of that sound. The thinner that rubber band is, the higher the pitch of that sound is going to be. A tension of a string, okay? You have the tension of a string being the idea that we have a really, really thick, or not really thick, but a really, really tight string, or a really tight rubber band, and then a rubber band that's not so tight. With a tight rubber band, you're going to get a higher pitched string, just like on a higher pitched note, just like you would on a stringed instrument. With a really loose rubber band, it's going to have more of a low pitch. And then you think again, okay, what happens if I want to play my piano loud? Okay, I hit the keys really, really hard. I add more energy. And if I want to play my piano really, really quietly, I don't hit the keys quite so hard, and it's going to produce a softer note. So when I talk about loudness versus quietness, it has everything to do with how much energy is in that one particular amount, right then and there. When I talk about pitch, the length, the thickness, the tension, all of those are going to be looking at the idea of how dense, how close together are these particles, or how far apart these particles are spread apart. So we're going to watch this video real quick. And what this video is going to focus on is this essential question for today. How are sound waves affected by changes in amplitude and frequency? So this is going to be the gist of this, which we've already talked about those two properties, but they're going to then add to it basically how we get pitch versus volume.
Whoa, Sam! That sculpture's amazing! How do you balance all those things?
Just gotta be very careful. Oh, no!
That jackhammer's making the whole table shake!
Yeah, I know! It's so loud I can feel it!
Phew, it stopped. But not before ruining your sculpture. Sorry, Sam. Just goes to show, sound is more than just what you hear. It's a whole world of vibrations.
How can sound be vibrations? It's noise.
Check it out. When you clap your hands together, or when that jackhammer hits the ground, it makes air move. In waves. Sound waves, to be exact.
Like ocean waves?
Well, kind of. Sound waves travel through the air, but they carry energy like ocean waves do. That energy is what makes an echo.
Really?
Definitely. When moving sound waves hit a surface, like a mountain or even a wall, the energy bounces off and comes back at us. That's the echo.
Cool.
But there's much more to sound waves than just energy. They have different pitches, frequencies, and volumes.
Huh? You're losing me.
Okay, think about the gazillion sounds around us.
Yeah, like birds sound totally different from gorillas, and tea kettles sound different from tubas.
Right. Their sounds have different pitches, high and low.
So what makes them that way?
High-pitched sounds have a high frequency. That means their sound waves vibrate quickly, and there are lots of waves per second, so we hear a higher pitch.
And low-pitched sounds have a low frequency?
Right. Fewer waves per second.
Well, that jackhammer was definitely low, but it was also loud. Wouldn't that make it a high frequency?
Not quite. Volume's a totally different thing. It's the loudness or softness of a sound. The louder the volume, the higher the wave. That's called amplitude.
Like altitude, only for sound. So, how loud is that jackhammer? I mean, compared to other things.
I'd say it's about 105 decibels.
Decimals?
No, decibels. Volume's measured in decibels. The louder the sound, the more decibels. An airplane taking off is 140 decibels, and a crying baby is 110.
Whoa, no wonder my little cousin gives me a headache. I gotta teach him how to whisper.
Yeah, a regular conversation's about 65 decibels, but whispering's only 0 to 5.
Hey, are there any sounds that are lower than 0 decibels?
Yep, humans can't hear them, but we think animals can. They're caused by giant explosions or waves in the ocean. In fact, scientists are studying them.
For what?
To help us predict when a volcano might erupt or if a tsunami's coming.
I can't believe how much goes on behind the scenes when it comes to sound. Who knew that sounds are vibrations that travel in waves, and that frequency tells us the number of waves in a second? It makes sense that frequency goes with pitch, or the highness or lowness of sounds. The volume of a sound is how loud or soft it is, and is measured in decibels. High sounds, low sounds, birds, and bass guitars.
Speaking of noise, it sounds like that jackhammer's done for the day. How about I help you put your sculpture back together?
Wow, thanks. That'd be great. I'll just put on some music.
Sam, remember what happens in loud sounds?
All right.
Okay, so let's go ahead and take a quiz and see how you guys do. So each one of these are going to be A, B, C, or D. What role does energy play in sound? If you think it's sound waves have nothing to do with energy, A. B, if you think sound waves carry energy. C, if you think energy is present in loud sounds only. Or D, energy is present in high-pitched sounds but not in low-pitched sounds. Okay? The correct answer should be B, sound waves carry energy. What is an echo? If you think it's the number of sound waves in a second, it's A. If you think it's the loudness or softness of a sound, B. If you think it's sound waves that bounce off a surface, C. Or if you think it's the highness or lowness of a sound, D. And it should be C, sound waves that bounce off a surface. What sort of frequency do high-pitched sounds have? If you think it's high, it's A. If you think it's low, it's B. If you think it's medium, C. And if you think it's no frequency, D. If there's a sound, there is a frequency, okay? And if it's a high-pitched sound, it has a high frequency. What does volume measure? If you think it's the speed of a sound, A. If you think it's the speed of a sound, A. The frequency of a sound, B. The highness or lowness of a sound, C. Or D, the loudness or softness of a sound. And the correct answer should be D, the loudness or softness of a sound. What causes sounds that are lower than 0 decibels? If you think it's low frequency, A. If you think it's high volume, B. If you think it's giant explosions in the ocean, C. Or if you think it's gametophytes, D. And the correct answer is giant explosions in the ocean, letter C. Which two aspects of a sound go together? If you think it's A, pitch and frequency. If you think it's B, decibels and pitch. If you think it's pitch and volume, it's C. And if you think it's amplitude and pitch, it is D. And the correct answer is going to be pitch and frequency. What does amplitude measure? Okay, if you think it's A, frequency, A. If you think it's volume, B. If you think it's pitch, C. If you think it's echoes, D. And amplitude, if you think about it makes the noise very loud, so it's volume. And if you answered all those right with me, then you got 100%. Okay? So let's go on, and with our notes, you're going to see it's a little bit different. I'm going to basically provide you all the information on the screen, and then what you're going to do is fill in those blanks. So there might be one or more words that you need. There's definitely one, but there may be more than one. So make sure that you're filling in everything as we go. Okay, so just a real quick review about sound waves here. A sound wave is a mechanical wave, and I've circled the word me in each one of these because mechanical starts with me, medium starts with me, and they have to have a medium in order for them to travel. We talked about this not being able to happen in space because there's no liquid solids or gases. There's a vacuum, and there's no particles there, or very, very few particles a long ways apart. A sound wave is also considered to be a longitudinal wave. It can also be a transverse wave, but when we're looking at a longitudinal wave like we see in this animation here, we're looking at the particles moving back and forth in this general direction, left to right. And so when we look at this, this is how it would travel in gases, and it would also travel in liquids this way. A transverse wave is going to travel through a solid as a sound wave. Okay? So if you look at this picture at the very top, it's not on your paper, but all these little dots represent atoms. And so you have to think about this as the air particles that we can't see around us. The closer that these dots are together, okay, the higher the pressure, the farther apart these dots are, the lower the pressure. And that's all caused by the sound as it moves through the air itself. Now, what you're looking at here looks almost more like a barcode, okay? But these barcodes are just representing where those dots are closer together in this case. So these are three areas that we have that are considered to be compressions. On your paper, you're going to have to identify a compression as letter A, letter B, or letter C, and fill in those blanks, okay? Compressions are where you are pressing those particles. In this case, those lines look like they've been pressed together, and they're crowded, okay? There's not a lot of space between them. But then, if I look at these areas here, okay, the four that I have circled, these are where we have rarefactions, and rarefactions are just the opposite of a compression. Still part of a longitudinal wave, but here, those particles are spread apart. Okay, so identify that as letter A, B, or C. And then finally, at letter A, B, or C is going to be wavelength. And when we look at wavelength in a longitudinal wave can be from rarefaction to rarefaction. This is one wave cycle as we talked about. This is a second wave cycle, so there's actually two wavelengths here. Or it could be from one compression, okay, here's one wavelength, to the next compression. Here's your second wavelength. So it can be from that, from one part of that wave to the next same part of the next wave, considered to be a wavelength in this. So I want to stop part one right here, and we're going to pick up part two with the rest of the notes.